everyone. Welcome into lecture number 10 of differential equations. This lecture is on the Wronskian. So let's start with some setup here. Remember, we've been studying second order linear differential equations. So let me write this out. We've been studying second order linear differential equations, and these are of the following form. So they come in the form y double prime plus some function p of t times y prime plus some other function q of t times y equals, and we've been studying homogeneous equations, but let's just say for the sake of the second order linear differential equations can equal any function g of t on the right hand side. So this is, again, a second order linear differential equation. So what I'd like to do now to start this lecture is introduce the idea of a differential operator. So a differential operator, we're going to study one in particular, but a differential operator is like a function that operates on other functions. So this is a function in some sense whose domain, so I'm kind of simplifying the definition. This is not a definition, this is just a basic idea here, but whose domain is a function space itself. All right, and its codomain is also a function space. So is another function space. So the basic idea here is that a differential operator is going to take in a function. It's going to basically perform some kind of derivative. That's where the differential comes from. But it's going to perform some kind of derivative on the function and spit out a new function, right? And there's one in particular that we are going to study in this lecture. First of all, we're going to build a special one out of a basic one, right? So the basic derivative operator in this case, so for this lecture, is just going to be called D. So this operator is D, and so let's just forget about the whole, domain, what has to be true about the functions, but basically this operates on differentiable functions. So D of phi is just going to equal phi prime. So all D does is take a derivative of phi. So this function phi is a function of t, and D is the time derivative in some sense, right? So D in this case can be thought of as just d by dt. So one derivative with respect to the t variable. All right, so what we want to do is, to kind of save us writing here, is we want to define an operator, a differential operator that will give us the left-hand side of our differential equation. So we define an operator as follows. We'll call it L. L is going to be equal to d squared plus, and I'll write out exactly how this works, but d squared plus p of t, so some function p of t times d, plus some function q of t times I. All right, so we know what d is, we need to know what I is, all right? And then we need to know how this whole thing operates all together. But here I is just the identity operation, that's why I called it I. So I of phi is just going to take no derivatives in some sense of phi, right? So it's just I of phi is equal to phi, and d squared, you can probably guess, of phi, what could this possibly mean? Well, this is function notation, so this means d of phi, and so this is a nested derivative, so this just ends up being phi double prime, right? So d squared is the second derivative operator. Now, how does this whole thing work? Well, just as it looks, right? So then L of phi, in this case, is just going to be all of this applied to phi, right? So it's going to be, I'll write it out in a couple steps, but we're going to streamline this as we move forward. But so it's d squared plus p of t times d plus q of t times I, all applied as an operator to this function phi. And so everything here is going to distribute, and we're going to end up with d squared phi, that's the second derivative, plus p of t, some function, times d of phi, so there's our first derivative, plus q of t times I of phi. Okay, and so again, we know what these things do, so this just gives us back phi double prime plus p of t times phi prime plus q of t times phi, right? I of phi identity. So there you go. So this ends up being the left-hand side of our linear differential equation up here. And the benefit of all of this setup is that now we can write the following. So we can write L of y equals 0 to represent, or equals g of t, I guess, in the terms that we've set up here, right? So we have a g of t, a general g of t up here. So L of y equals g of t to represent our second order linear differential equation. Okay, so this is just some notation to get us started here. Our second order, so we are going to study, like I said, homogeneous equations throughout this lecture, but we're also, I mean, not specifically, so I kind of was pushing toward homogeneous equations there, but not necessarily. But I want to remind us what a second order linear initial value problem looks like. Okay, so recall that for a second order differential equation we need two pieces of initial data for an initial value problem, right? So let's just recall that a second order linear initial value problem is of the following form. So we'll continue to use our L here. This L, it's going to be, so L could mean, you know, a lot of different things, but we're going to have our L always mean for this lecture this differential operator. Okay, L equals d squared plus p of td plus q of ti. All right, so the form of our initial value problem is now going to be L of y equals g of t. There's our differential equation, right? Second order linear differential equation. The initial values have to then be y of t naught equals some value y naught and y prime at t naught. So those are the two initial values, y at t naught and y prime at t naught. And we'll just call this one y naught. Okay, so all of this leads to, all of this setup here is for us to be able to state a very important theorem. Okay, and this theorem is an extension of the fundamental existence and uniqueness theorem. Okay, so this theorem is going to be an FEUT for second order linear initial value problems. Lots of abbreviations here. So fundamental existence and uniqueness theorem for second order linear initial value problems. Okay, so here is the theorem. Again, very important theorem. We're not going to prove this, but we definitely need to state it. All right, so this one says, let's let P, Q, and G be continuous functions that are all continuous on an interval containing a point t naught. So we'll say on an interval I containing t naught. So t sub 0. All right, and let's let, I'll just rewrite this, but let L of phi, we can just write this as just let L. Let's just let L equal our differential operator, right? So d squared plus p of t d plus q of t I. Then the initial value problem, the IVP, which we just wrote down, but I'll write it again. So L of y equals 0. L of y equals g of t. L of y equals g of t. So this function here is continuous at t naught, just like the two coefficient functions. So the g of t, and then y of t naught equals y naught, and y prime at t naught is equal to y prime naught. This has exactly one solution. So this initial value problem, this is the fundamental existence and uniqueness theorem. So it has exactly one solution, which we'll call phi equals phi of t, and the solution is defined on an interval that's at least as large as I. So the solution is defined on an interval at least as large as the interval I, that which, remember, the interval I is the common domain of P, Q, and G for which that it contains T naught and for which these functions are continuous. Okay, so again, fundamental existence and uniqueness. There, it has a solution, that's existence, has exactly one solution. That's uniqueness, right? So it has a solution and it's unique. As long as the coefficient functions are continuous on an interval containing the initial point, right? And containing this the initial t value, I should say, containing the initial t value. All right, so this is a natural extension of the FEUT for linear first order differential equations. So this is a natural extension of what we call the FEUT-L, right? Okay, so let's use this now, do a couple of straightforward examples to start out, and then go from there. So here's an example. I would like to, without solving this differential equation, but find an interval. So when I say find an interval, let's say it this way. Find the largest interval that the solution is guaranteed to exist. So that the solution is guaranteed, and by guaranteed I mean guaranteed by the fundamental existence and uniqueness theorem. All right, so this one is going to be, for this, I need to give you an initial value problem now, right? So this one I'm going to give you t minus 2 y double prime plus y prime plus t minus 2 tangent of t times y equals 0. So this one is homogeneous. Y of 3 equals 1, and y prime of 3 equals 2. All right, so take a moment, think about this one, try to find the largest interval that the solution is guaranteed to exist without solving this, without actually trying to solve for it, for the solution, but just apply the fundamental existence and uniqueness theorem and find that interval. So I'll check in with you when you guys are done. Let's see how you did. First of all, this is not in the right form, right? So this is not the kind of linear operator that we've described up here. Our linear operator has to be d squared plus p of t_d plus q of ti, right? It's not right now. So what we have to do first is divide everything through in this equation by t minus 2. And so this equation will become y double prime plus 1 over t minus 2 y prime plus the t minus 2's cancel here, right? So tangent of t times y equals 0. 0 over t minus 2 is just 0, right? And so now we can identify our functions. Our p of t is this 1 over t minus 2, and the domain of this function, right, is all real numbers except for 2. So any real number except for 2 can go into this, right? What about the q of t function? Q of t is equal to tangent t. And tangent t, the domain, is that it cannot equal pi over 2, 3 pi over 2, etc., right? So the domain of q, we'll say in this one, is equal to, I'll say it this way, t is not equal to, so I'm just going to tell you the points it can't be, right? It's all the t except for the values which correspond to asymptotes for the graph of tangent of t. So this is going to be pi over 2 plus or minus n times pi. All right? So those are all the points that are not in the domain of tangent. It's continuous everywhere else. And what about our g? Our g of t is still 0, right? G of t is equal to 0. And so the domain of g is all real numbers. Okay? And so the largest interval for which the solution is guaranteed to exist, guaranteed by the FEUT, is the overlap of these domains, these three domains, which contains the initial value, right? The initial point. And so the initial point here is t naught equals to 3. So t naught equals to 3. So we can just do this by inspection, right? So pi over 2, that is going to be like around 1.5. 2 comes next, 3. So the next bad point is going to be 3 pi over 2. 3 pi over 2 is bigger than 4, right? So definitely bigger than 3. And so the domain is going to be, so the largest domain is going to be, I'll plot it on a number line here kind of. So we have pi over 2, we have 3 pi over 2, We have our initial value 3, which is maybe around here. But we also have this point 2, which is not allowed, right? So let's say it's around here. And so just based on this picture, and probably poorly proportioned, but that's okay, our largest domain that we can have is just this domain between these points, right? And so the largest domain of the solution of this differential equation, without even solving it, we know that the largest domain that we're guaranteed, or you could almost say the smallest domain that's guaranteed, right? But the largest interval that is guaranteed by this solution here is t has got to be between 2 and 3 pi over 2. Okay, so the domain is between 2 and 3 pi over 2. All right, so hopefully you guys got that one. And here's another one. So this one I'd like you guys to solve. So this is item number 3. Find the solution of this differential equation. This initial value problem, I should say. So find the solution. This one is, it's got some generic coefficients. So y double prime plus p of t times y prime plus q of t times y equals 0. All right, so homogeneous equation again. The initial conditions are y of t naught is equal to 0, and y prime of t naught is also equal to 0. All right, so take a minute, think about this differential equation, think about, we haven't talked about a whole lot of methods for solving these kind of differential equations, but think about what the solution could be, and then apply the fundamental existence and uniqueness theorem to show that that's what the solution is. Okay, I'll check back with you guys in a minute. Okay, now that you've had a chance to work it out, let's see how you did. So first of all, if the initial conditions are both 0 and 0, then one function that satisfies this, right, we'll guess, is the function y of t is just simply equal to 0, the 0 function. So it is differentiable. Y prime of t is, of course, equal to 0, right? And therefore, y and y prime, so in other words, the initial conditions are satisfied, right? So the initial conditions are satisfied. And not only that, but the second derivative, the third term here, the second derivative is also going to be 0. And when we plug in, then the differential equation, right? The differential equation is also satisfied. So the 0 function is a solution of this initial value problem. Now, as long as these, so I should have said this, right? So as long as these coefficient functions, p and q, are continuous, right? So if p and q are continuous on R, right? So on the entire real line, or at least on an interval containing t naught. So, or at least on our interval containing t0, the initial t value, right? Then the solution must be unique. So the solution is unique. All right? Now, if the solution is unique and we know that y equals 0 is a solution, then guess what? Then y equals 0 is the unique solution. So then y equals 0 is actually the only, right? The only solution of this differential equation. All right, so that's kind of a tricky one, and I guess I didn't give you all the information at the outset there, but hopefully you noticed this, right? That if p and q are continuous, then you could apply the FEUT. All right, before we get to some more examples here, let's state another theorem. So this theorem is called the theorem of superposition of solutions. So we'll just call it superposition. So this one says the following. So let's let our differential operator be the same one we've been working with. So L equal to d squared plus p of t times d plus q of t times I. All right. If y1 and y2 are both solutions of the homogeneous differential equation. So if the differential equation L of y equals 0, then the linear combination, so the function y of t equals c1 y1 of t plus c2 y2 of t is also a solution for any constants. So in this case we'll say real constants c1 and c2. Okay, so as an exercise, I want you guys to prove this one. So this is a recommended exercise to prove this theorem. So what do? Well, you assume that y1 and y2 both solve this equation right here. You plug in this new function and you apply the differential operator to this new function and take advantage of the fact that these two are both solutions. Okay, so you should be able to just work that out, basically just write it out, and all the details should fall right out of that. It should be very straightforward. But definitely verify it. And it's an important theorem because this is, you'll see exactly why. But it's an important theorem that we're going to work with as we move forward to build our general solution of our differential equations as we go forward. Okay, so this does beg the question though. So if we have two solutions and we can add them together and get another solution, is this solution different, right? Or are these two solutions that we started with, are they different solutions? Are they the same solution? Where does the fundamental existence and uniqueness theorem come into play for this kind of situation? All right, and so let's consider the following. So let's consider some initial values for this problem. So let's consider the following setup. All right, let's say we have initial value problem. So we'll write it as L of y equals to 0 with y of t naught equal to y naught and y prime of t naught equal to y naught prime. All right, and let's suppose that y1 and y2 are two solutions of this initial value problem. So of this IVP, initial value problem. All right, then if y equals c1 y1 plus c2 y2 is going to be a solution, right? So if it's a solution of the initial value problem, then it must satisfy the following. So then I'll say this following. So the constants C1 and C2 must satisfy the following system. So on one hand, y of 0, right, equals C1, C1 y of 0. Sorry, this is not what I meant to do. I meant to do y of t naught. Okay, so y of t naught is equal to, on one hand, c1 y1 of t naught plus c2 y2 of t naught, which, remember, these both solve the initial value problem, right? So, but anyway, this has got to be equal to y naught, right? And on the other hand, y prime of t naught has got to be equal to c1 y1 prime of t naught plus c2 y2 prime at t naught, and this has got to be equal to y naught prime. All right, and this whole system now, so if we ignore these two, but just look at this half of the system, this system can be written in matrix form. So this system can be written as a matrix product. All right, and so if we just take the coefficient matrix here, we can call this, I'm going to call it W, but this is going to be y1 of t naught, y2 of t naught in the first row. In the second row, it's going to be y1 prime of t naught and y2 prime at t naught. The unknown constants form the vector here, C1, C2. And on the right-hand side, the unknowns are y0 and y0 prime. Okay? And so this can be solved by Cramer's rule. All right? So this can be solved by using Cramer's rule. So we'll call this matrix W. And then this is just our vector C, and our vector, this is our vector of initial conditions. Let's call it B. So this system, W times C equals B, right? This can be solved by Cramer's rule, provided a couple things happen, right? So remember how Cramer's rule works. Cramer's rule says that the solutions of this system, C1 is equal to, I'll just write these down and then we'll remember what they are. But the determinant of W1 over W, or the determinant of W, and C2 is equal to the determinant of W2 over the determinant of W. All right, where we already know what W is. So W is this matrix here. So W is equal to our matrix of these initial values of the component functions here. So y1 of t0, y2 of t0, y1 prime at t0, y2 prime at t0, right? W1 is the matrix that you obtain by replacing the first column of W with the right-hand vector B here, right? So this is going to be y0 and y0 prime. So the initial values over here, and then y2 at t0 and y2 prime at t0, those remain the same. All right, this one needed a prime. And then same thing for W2. W2, this is going to be the matrix that you get by replacing the second column with the initial value column vector here and leave the first column alone. So y1 at t0 and y1 prime at t0 stay the same. The initial values y0 and y0 prime go here. All right, now in this whole setup, these just come from Cramer's rule, right? So you'll take the determinant, that's just that crisscross product, right? So this times this minus this times this. This times this minus this times this. Those are in the numerator though, so even if those are 0, it's not a big deal, right? And all these things are numbers here, so if they're in the numerator, they're 0, it's no big deal. But what would be a big deal is if this denominator became 0, right? So if the determinant of this matrix W became 0, or it was equal to 0, that would be bad, right? So this system I wrote up here can be solved by Cramer's rule, and then we have to say, so long as the determinant of W, which remember the determinant is that kind of crisscross product, right? So it's y1 of t0 times y2 prime of t0 minus y2 of t0 times y1 prime of t0 if this is not equal to 0. All right, and so that's the criteria for our two functions y1 and y2 to be potential to have the potential to be added together to make a linear combination to solve the initial value problem, right? So we can't even find the unknown constants if this determinant down here is equal to 0. If it's not equal to 0, we can always find the constants, all right? So that's the criteria. So the reason I called this W is because this is where the name for this section comes from. So these things are called, both of these in some sense are called the Wronskian of the two functions. So the matrix here, the matrix W, which again, so we can make this matrix, we can drop the initial point here, but let's just say y1 of t, y2 of t. So this is now a function, right? So let me write it this way. A matrix that depends on t. So W of t is equal to this matrix, and then the second row is y1 of t prime, y2 prime of t. So this is called the Wronskian matrix. All right, Wronskian matrix. And so this obviously depends on the functions, right? So it's of y1 and y2. And actually, what we probably should do for consistency here is put a hat on this. Let's put a little hat on this. So the reason I want to put a hat on it is because the Wronskian that we're going to refer to as just the Wronskian, that's going to be this determinant function, all right? So I'll say this. And the Wronskian, sometimes called the Wronskian determinant or the Wronskian function, but the Wronskian or Wronskian function of y1 and y2 is the determinant, right? So we'll call this one w of y1, y2. This is still a function of t, right? This is the determinant of w hat of t, which is this function that we get from crisscrossing, right? So y1 of t times y2 prime of t minus y1 prime of t times y2 of t. Okay, so these are the definitions, the main definitions here. So we have our Wronskian matrix, which is this matrix right here. So this is our Wronskian matrix. And then we also have our Wronskian itself, which is this function here. And so we're going to use this moving forward. All right, so let's state a theorem now. So this is item number 6, right? So here's our theorem. This one says, suppose that y1 and y2 are two solutions. So two solutions of our homogeneous second order linear differential equation L of y equals 0. And suppose, so these are solutions of the general equation, right? But now let's suppose that there's also initial data prescribed. So initial data y at t naught equals y naught, and y prime at t naught equals y prime naught. All right, this is prescribed. All right, then it is possible to choose, so this is just summarizing everything we just worked out. So it's possible to choose constants C1 and C2, real numbers, such that y equals C1 y1 plus C2 y2 is a solution of the initial value problem. So that this solves the IVP if and only if the Wronskian is non-zero. So if and only if the Wronskian w of y1, y2 of t, this function, right, is non-zero at t naught. Non-zero at t naught. Okay, so there's the theorem. That theorem summarizes everything that we just wrote down, that we just worked out. So the Wronskian, if the Wronskian is non-zero at the initial t value, so if the Wronskian at t naught is not equal to 0, then it means that we can solve the initial value problem using those two solutions that we found to the homogeneous problem before the initial values were prescribed, right? So the general solution in some sense. All right, let's do an example here. So I'll give you some information here. The functions y1 equals e to the minus 2t and y2 equals t e to the minus 2t. These solve the differential equation y double prime plus 4y prime plus 4y equals 0. So I want you to, number one, show that those are solutions, but also show that y equals c1 y1 plus c2 y2 solves the initial value problem for any initial data. In other words, you could find the c values, right, for any initial data. And so remember, our initial data here is y of t naught is equal to y naught, and y prime at t naught is equal to y naught prime. All right, so take a minute, think about the theorem we just wrote down, think about the statement of this problem, try to do it yourself, and then when you come back, we will do this together. see how you guys did here. So first of all, we need to verify that these two solve the differential equation. So I'm going to leave that up to you guys. So you should be able to do that. Just take two derivatives, plug in, everything should work out here. So that's a recommended exercise. Verify that those are solutions. All right, what we want to do now is verify that the linear combination of the two is going to solve the initial value problem for any initial data. And to do that, we're going to use this theorem, right? So we're going to use this theorem. So we're going to compute the Wronskian. So let's start with W hat. So our matrix W hat is built out of, remember, the first column is going to be function 1, e to the minus 2t, and its derivative. So the derivative is the second entry in the first column. So that's going to be minus 2 e to the minus 2t. The second column is going to be the second function, t e to the minus 2t, and then its derivative, right? So this is going to be a product rule. So it's going to be e to the minus 2t minus 2t e to the minus 2t. So there's our Wronskian matrix, right? Now, once we have the Wronskian matrix, then what we have to do is compute the determinant, right? The function. So we're going to multiply this times this, and then this times this, and we're going to subtract, right? So the usual matrix determinant, even though there's functions in here. So this is going to be e to the minus 2t times e to the minus 2t minus 2t e to the minus 2t minus this product. So that's going to be minus 2t e to the minus 2t times e to the minus 2t. I know it's kind of wacky the way that I wrote it there. But the whole point here is that now when we multiply this through, look what's going to happen. We're going to get e to the, you add these up, right? So e to the minus 4t. But then the rest of this is going to cancel because we're going to have, that's why I left it like this, right? E to the minus 2t times minus 2 e to the minus 2t. Same thing here. Subtract them, they cancel. So this is e to the minus 4t. All right? But the whole idea here is that this is e to the minus 4t. This is not 0, right? So this function cannot be 0. This is not 0 for any t in R. So for any initial t value, that's not going to be 0. All right? So as long as you do this first step where you verify that these two functions are really general solutions to this differential equation, right, to the general differential equation, then the Wronskian tells us, because the Wronskian determinant is not 0, right, then what we have here, so I have bad notation. So we need determinant symbols here because I just said that it was equal to the determinant, right? So because though that this can't be 0, that means that this solution, the linear combination of those two functions, will always be a solution of the initial value problem. You'll still have to solve for those constants, C1 and C2, but this tells us that it's going to be possible, right? It's going to be possible to do it. So that's what the Wronskian tells us here. That those two solutions are somehow different enough to, when they're combined in a linear combination, that they'll give us a solution to any initial value problem. All right, the idea of a Wronskian can be extended to 3 dimensions. I'm just going to do a very simple example, so just so we see how it works. But the idea of the Wronskian, it can be extended to many higher dimensions, okay? So this can be extended to higher dimensions. So here's how it works. The Wronskian of y1, y2, all the way up through y sub n. So we can do this for n functions. This is going to be equal to the determinant of the matrix. So the Wronskian as a function, right? The matrix whose first row is just those functions. y1, y2, y3, all the way to yn. The next row is going to be the first derivatives. y1 prime, y2 prime, y3 prime, all the way over to yn prime, and then it goes all the way down. We want to have n, it's got to be a square to take a determinant, right? So it's going to go all the way down to the n minus first derivative. So yn minus 1, y2 n minus 1 derivative, y3 n minus 1 derivative, all the way over to yn n minus 1 derivative. Okay, and so we take the determinant of this, that gives us a Wronskian of n functions. That's how you compute the Wronskian of n functions. So just to see how it works, let's compute the Wronskian of the functions 1, t, and t squared. Very, very simple. Probably couldn't get simpler with these functions, right? But it's going to end up being the determinant of, to build the matrix, the functions go along the first row. Their derivatives go along the second row, right? And the derivatives of those go along the next row. All right, and then we stop because we filled out a square matrix. So we have 3 functions. We take 2 derivatives. So now we have 3 rows and 3 columns, a square matrix. And remember how to take a determinant of a 3 by 3 matrix. You can copy, I mean, this is pretty straightforward, but you can copy, though, the first column to the outside, the second column to the outside, and then you do this process where you multiply the diagonals here, and you add those, and then you multiply the diagonals here, and you subtract those, right? And so when you work it out for this one, you're going to get 2 times 1 times 1. So 2 plus 0 plus 0 minus, then subtract these ones. That's a 0 plus 0, right? Plus 0. So this one's just 2. But 2 is obviously never 0, right? So as a function, this is a constant function equal to 2. So the Wronskian of 1, t, and t squared is just 2. Okay, so this is how you extend the Wronskian to higher dimensions. Okay, we're almost done. I just want to state one more theorem, and then we'll leave that there, and we'll call this lecture completed. So this theorem is, again, very important. It gets a name. It's called Abell's theorem. So Abell's theorem says the following. All right, this says if y1 and y2 are solutions of our second order differential equation, second order linear homogeneous differential equation. So if they're solutions of the equation, L of y, I'll write this out again, but remember what this means. Y double prime plus P of t, y prime plus Q of t, y equals 0, all right? Where P and Q are continuous. So P and Q are, in this scenario, continuous on an interval containing T naught, then the Wronskian of these functions of y1 and y2 is given by this formula. So W of y1 comma y2 at t is equal to some constant times e to the minus the integral p of t dt. So the coefficient on the y prime term. All right, and this is true on the entire interval containing t naught. All right, so on the interval containing t naught for which p and q are continuous, right? So in this scenario, the constant c, this does depend on the functions y1 and y2. So it depends on y1 and y2 and the order that they're given in. So y1 and y2, but it does not depend on t. So since it does not depend on t, then if this constant is 0 for y1 and y2, then the Wronskian is 0 for all points in the interval, right? And so there's the big conclusion here. So therefore, the Wronskian of two functions, y1 and y2, is either always 0 or never 0 on the interval. So on this interval I. So the I is the interval, again, the interval containing T naught for which P and Q are both continuous. Okay? So this is Abell's theorem. Again, it's just a nice application for us of the Wronskian. It's a formula, right? It doesn't give us the Wronskian directly, but it says that the Wronskian is given by some constant multiple of e to the minus integral p of t dt, where you don't even have to know the solutions to be able to compute that much of the Wronskian given your second order linear homogeneous differential equation, right? So I'm going to leave this lecture here, and I'll talk to you guys in the next one.